So in previous videos, we have introduced, we have explained what the geometric interpretation of decision variables and constraints are. So here we're going to continue to introduce the geometric interpretation of objective function. Now for that, I want to take another look at the production plan that we call it option 1 previously. So as we know, the associated profit for this option 1 is simply plug in the real number into this expression that we call objective function. So you plug in a times 500 plus 5 times 0, that's 4,000. Now the question I have for you is, are there any other options or production plans that can also produce a profit at 4,000? Realize to answer that question simply require us to get rid of the middle part. By that I mean, if we set up ax1 plus 5x2 equal to 5,000, this equation describes all the points, or in the context of galaxy industry, all the different production plans that should produce profit in 4,000. So in other words, this expression is the objective function here itself cannot be represented as a geometric entity in this two-dimensional space. However, if we force this expression to take on a particular value, in this case 4,000, the resulting equation becomes a line. We can find where the line is located by the method we used before. So the idea is just to find two distinct points that lie in the line. So we already know 500, 0 is in the line because that is what is demonstrated here. So let's just need to find another point that is also in the line. And again, for the ease of computation, we can always force x1 equal to 0. So that gives 0 to this term, and that requires x2 to be equal to 800 in order for the equation to hold. So these 2 points should define where the line, where this line is. So 500, let me again change to a different color. So 500, 0 is here, and 0, 800 is somewhere. The 600, 700 is somewhere here. So let me just use a line to connect the 2 points. So be from here to here. Alright, so this is a line that is corresponding to this equation. So now this line is providing the answer to the question I asked earlier. Are there any other production plans that can also produce $4,000 in profit? And the answer will be all those production plans that is represented in this segment from here to here. And there are actually infinite number of production mixture that can produce $4,000 in profit. And those plans that represented outside of the feasible region, of course, they are not feasible because they violated at least one constraint. So this segment is not feasible. This segment is not feasible, and the segment in between are the feasible solutions. There are infinite, many of them, and what they share in common is they all produce profit. they all produce profit equal to 4,000. So I call this line the line of same profit. Now, so we have addressed this part of the objective function. So what about the stipulation of we are trying to maximize the profit? So I just draw another line of same profit while you are busy returning your text message. So this profit is equal to 1,600, and I use the exact same method that I showed before. So there are two observations associated with these two lines. One is they are parallel. The other one is the profit increase in this direction. Both observations should not come as a surprise, because the reason they are parallel is if we rewrite this equation into the intercept slope format, meaning if we rewrite it this way. So in this case, x2 is what is commonly denoted as y instead of x. So it will be plus 4,000. And then if we divided both sides by 5, it will become. So we call this way to write the same equation the slope intercept format. So realize 4,000 or any arbitrary profit we try to enforce does not affect the slope of the line. Therefore, all the resulting line will be parallel to each other. And the second observation is it increase in this direction. Again, it should be quite intuitive because the profit increase as the number of space rays increase. Similarly, the profit increase as the number of zapper increases. So that corresponding to this direction and that direction. So that overall, this direction is corresponding to an increase line of same profit. So these two observations should help us realize what is the solution, or how to find the optimal solution that can produce the highest profit. So the solution will be try to find the line of same profit, try to push the line of same profit towards this direction as far as possible while maintaining contact with the feasible region. So that particular line of same profit will therefore go through this particular extreme point. So let me draw this line. Again, remember it's going to be all the line of same profit are parallel to each other. So that's the line. Let me extend it to the other direction. So this is a line of same profit that associated with the maximum profit achievable. And this corner point, this extreme point, is the optimal solution that we are looking for. So in order to find this optimal solution, we just need to find the coordinates that are defined by the intersection of these two lines. So you can do this by set up this so-called system of equation. The 2x1 plus x2 equal to 1,000 corresponding to this line, the green one. The second equation, which is the time constraint corresponding to the red one. So you set up these two equations and then you can solve for the solution, which turn out to be x1 equal to 320, x2 equal to 360. So once you plug in these two numbers into the profit expression, you should be able to identify the maximum profit achievable is 43.60. Therefore, this line is corresponding to the profit equal to this value. And the coordinate of this point is 320, 360. So if you have trouble to solve this type of system of linear equation, you can always Google solving system of linear equation. And there are lots of websites that provides great examples and practice problems that you could work on by yourself. Now I want to add the third observation about the optimal solution, which is the interior point cannot be optimal. And the reason is pretty self-explanatory, because if it's a point here in the middle, you can always move towards the direction that would lead to a increased profit in this case. So that's the third observation. So by now we have completed the geometric interpretation of objective function, and through that we have found the optimal solution, which is to produce 320 dozens of space rays and 360 dozens of zappers. So next, I want to introduce to you another topic called sensitivity analysis. So it is also referred to or known as what-if analysis. So essentially, it's asking a bunch of what-if questions, such as, what if the $8 per dozen profit margin for space rate decrease? And what if we can acquire additional plastics for manufacturing? And what if we have fuller constraints? So this kind of what if questions and how those variation would affect our optimal solution and also our maximum profit. So in the next few minutes, I just want to give you some overview of what those what-if analysis entails. Details will be provided in next segments of lecture. So imagine if instead of ax1 plus 5x2 as the profit expression, if recently we found that the profit for space rate has dropped from $8 to $5, so the new profit expression become 5x1 plus 5x2. So how would that affect the profit or the optimal solutions? And earlier I already told you that once the slope of the line of same profit is really determined by the ratio of the two profit coefficients. So if this change to this new ratio, what would happen is the orientation or the slope of this profit line of same profit would, in this case, would actually turn counterclockwise. So imagine what would be the potential impact to the optimal solution. And earlier I suggested in the third observation, the interior point cannot be optimal solution. And also in this particular case, we know that one of the extreme point is the optimal solution. So out of 5, we have 1, 2, 3, 4, we have 4 extreme points. One of them is the optimal. So the question I have for you now is, can boundary point become an optimal solution? And that the answer to that is actually related to the sensitivity analysis regarding to the profit coefficient. So imagine if you reduced the space rate profit to a certain degree, this line of same profit might turn enough to coincide with one of the edge. So in that case, the whole edge will become optimal solutions. So I'm almost running out of space on this whiteboard. Let me use a PowerPoint slide to continue our brief overview of what if analysis. And so here we have 2 additional constraints. By the way, this is actually the full example of galaxy industry used in the textbook. So we have the first additional constraint is concerned with total production and is corresponding to this line. And the feasible half space is on this size. So notice that this constraint does not further reduce the feasible region because it does not intersect with the feasible region. Therefore, it's called redundant, meaning if we don't have the constraint, the feasible region will stay the same. On the other hand, the second additional constraint is represented by this line, and it does cut into the existing feasible region. So this triangle used to be feasible, now it's no longer feasible after we add the 4th constraint. And then the third type of what if analysis is concerned with what if we can acquire additional plastic, for example. So geometrically speaking, if we increase the right hand side of this inequality, the associated equation will move parallelly. So for example, if we increase this 1000 to 1100, then the corresponding line, which is this one, will move in this direction by a certain amount. So as a result, the feasible region increase. And earlier I mentioned that by changing the profit coefficient, this dashed line, which is the line of same profit corresponding to the highest profit, the line of same profit, the orientation will change. So for example, if we change the coefficient to a certain degree, the line of same profit might have this new orientation. But in this particular case, if we turn it that much, this corner or this extreme point will still remain the optimal solution. But if we turn it further in the counterclockwise direction, then it is possible that we might end up with a line of same profit that has this orientation. And if this is the case, the farthest we can push it to will be the place where it coincides with one of the edge. So as a result, the whole edge, which consists of infinite optimal solution, would all produce the same maximum profit. And then if you turn it further this way, the line of same profit become oriented this way. So as a result, you can, if you push all the way to the farthest, you realize in this case the optimal solution becomes this particular extreme point. I will highly encourage you to replicate this graph using a piece of paper and a pencil from scratch, because the solid understanding of the geometry here is really critical to the understanding of sensitivity analysis. which is the topic we're going to introduce in more details in the next video.